Hi, I'm Bob Rau. I'm with Hewlett-Packard Laboratories. I'll be talking to you today about instruction-level parallelism, or ILP for short. In a companion lecture to this one, we looked at how ILP is exploited by ILP compilers, working our way through from local scheduling at the single basic block level through to global scheduling. In this talk, I want to focus on the other two major aspects of an ILP compiler, namely exposing enough ILP for there to be something to be exploited in the first place, and then enhancing the ILP if that is inadequate. I'd also like to get into some of the ways in which engineering an ILP compiler turns out to be quite different than engineering conventional optimizing compilers. Exposing ILP consists primarily of eliminating spurious dependencies that shouldn't be there in the first place. The general rule is if you eliminate as many dependencies as possible, then your data dependence graph becomes more and more parallel. There are two ways in which we have spurious dependencies. One is through the use of registers by operations, which leads to things like anti and output dependencies. And the second mechanism is the analogous one through the use of memory locations. Now, the technique that is used to eliminate anti and output dependencies due to register usage is called register renaming. And here we look at it in the context of a control flow graph. So we are looking at the global problem of multiple assignment. What we have here is a control flow graph in which the variable t is assigned to twice, once over here and once over here. And in addition, it is used twice, once over here, once over here. Now, in this diagram, the heavy arcs correspond to the flow of control between basic blocks, whereas the red arcs correspond to the dependencies, the data dependencies in the program. Because t is used here and consumed here and here, we have flow dependencies from the definition to the two uses. And similarly, we have a flow dependence from this use, from this definition to this use. Now, these flow dependencies are inherent to the program. You cannot remove them. However, in addition to that, we have an anti-dependence between this use of t and the subsequent definition of t. Now, this is a problem because it might turn out that in the course of scheduling, it would have been preferable to have interchanged the order of these two operations. But in fact, because of the anti-dependence, that will not be possible. So what we can do is resort to the standard technique of renaming, make every definition of t go to a different virtual register, which we'll call t and t2. Now, this use of t will refer to this, whereas over here we run into a bit of a problem, because if we came down this path, then we would want to use t, whereas if we come down this path, we would want to use t2 to get the same effect that we got over here when we refer to t. The way this is handled is by introducing a hypothetical function called a phi function. And what that does is it renames either t in this case or t2 to be a third virtual register t3, and it's t3 that we use. So the net result is that if control comes down this way, we end up using this. If it comes down this way, we end up using t2. So by virtue of this hypothetical function, we eliminate the anti-dependence that existed over here, and we now have the liberty to change the order if that turns out to be useful. Now, what I won't get into is how one actually implements these phi functions. In effect, one has to either rename all of these back to be the same variable, in which case the phi function disappears, or one has to insert copy operations. And there are various pros and cons that surround that issue. Now, the trouble is that even though static single assignment, which we just saw, eliminated antidependencies in an acyclic case, it doesn't work in the cyclic case. Here's a case where we have a loop back on this basic block. Once again, we have two definitions of T and two uses of T. And because we have a definition that follows the use, we have an antidependence over here, which once again we'd like to get rid of. Now, if we try and use static single assignment, what we will need to do is insert a phi function over here, which combines the two definitions that can reach this use of T. So one definition that reaches it is T1, and the other definition that reaches it is T2 from the previous iteration. And these two can be combined, renamed as T3, and that is what we will use out here. As a result of this, we have in fact got rid of this antidependence, but we end up introducing two new antidependencies. The reason is that over here, we define T2 and it's used over here. So there has to be an antidependence here. And secondly, we define T3 over here and we use it over here. So there has to be an antidependence that spans an iteration from this use to this redefinition. The fact is that in cyclic code, we just have to keep revisiting the same operation again and again. As a result, there's no way of avoiding the constant redefinition of the same variable, regardless of how we rename it. So to get around this, we have to enrich our concept of virtual registers and go to what is called an expanded virtual register. In this scheme, each virtual register is replaced by essentially an infinite number of virtual registers, one of which is unique in that it is being pointed to. And by convention, the one that is being pointed to, we will refer to as T subscript 0, or by convention just T. The ones below that we'll refer to as T1, T2, T3. Now, the way this works is somewhat like a push-down stack. Between every two assignments to T, we will do what is called a remap operation, which in effect moves this pointer up by 1. And so over here we assign to T, but when we do a remap and we come here and assign to T again, we really get a different virtual register. As a result, since we always assign to distinct virtual registers within this one expanded virtual register, all of the old definitions are available and can be referenced by using a subscript. In general, the subscript tells you how many definitions ago you want the value for. Now, with this kind of a scheme, we can eliminate the antidependencies that we had in the cyclic case. So what we do here is between successive redefinitions, apparent redefinitions of T, we remap T. And so each definition of T is really going into a distinct location in the expanded virtual register. And when we reference T, since there's a remap between the definition and the use, we will reference T square bracket 1. Also, to make sure that when you reference T square bracket 1, you can get either this definition or this definition, we'll rename this to be T1 and the use to be T1 as well. So by adding this additional kind of fantasy, as it were, of these unlimited virtual registers, we can get rid of antidependencies in acyclic code as well. Now, it might appear to be unrealistic to have these expanded virtual registers. In fact, it is no different than the unbounded number of virtual registers we already have grown accustomed to. In both cases, there's only a limited number of those virtual registers that are live at any one point in time. And those are the only ones that need to be allocated to registers. And whether it is conventional virtual registers or these expanded virtual registers, that's what we resort to eventually. I just want to add in passing that whether or not you have specific hardware support to support this remapping capability, it is possible to implement this kind of a code in when it comes time to generating the code. Now, the second type of dependencies that we get, spurious dependencies, are as a result of loads and stores to locations in memory. Over here, filtering out all the rest of the operations other than the loads and the stores, we get a sequence in the original sequential code of various stores and loads. And what this store is saying is that the contents of this virtual register V1 are to be written to address A1. And this one is requiring a load from memory location A2. Now, when we have no information as to whether A1 and A2 are equal or not, we have what is called a maybe dependence. Because A2 may be the same as A1, we don't know whether in fact it is or not. And so what we do is we put in a flow edge with a question mark on it, indicating that there could be a flow dependence here, but we are not sure. If these two ended up being the same, there would be a flow dependence for sure. Now, in this situation where we have no information about whether the addresses are equal or not, there is little parallelism that can be found, except over here where we have two loads that are sandwiched between these two stores. And these two loads can be made independent of one another. So the dependence graph that we get looks like this. There's essentially a serial dependence that runs through all of them, except that these two loads are in parallel. Now, imagine that as a result of some analysis, we were able to prove that A3, A4, A5, and A6 were all pairwise unequal. So in that case, these dependence edges between these four operations would all disappear, because now we are certain that these stores and loads are not to the same location. Now, as a result of eliminating this output dependence between these two, and these two being potentially in parallel, what we have to do is we have to move the ambiguous flow dependence that used to come from here, and we'll have to get it coming from the first store. Similarly, this maybe anti-dependence goes down over here, likewise over here. In addition, if you consider this load, it used to be anti-dependent only on this store. Now that these two could potentially be in parallel, we have to make this store anti-dependent on it as well. So we'll have to add an additional edge to represent this more parallel graph. And we get, as a result, this graph over here, where in addition to those two loads that were independent, we also have two stores that are independent. But in the process of getting to this, we ended up with two additional edges. Now, two additional edges may not seem that bad, but in the worst case, if we were able to prove that all the stores were independent of one another, but were not able to prove that any of the loads were or were not independent of any others, the number of edges that we'd have would be approximately the product of the number of stores and the number of loads. Now, in a fairly large program, that number of edges can become very, very large. And this is going to be a problem that will resurface when we talk about engineering ILP compilers. For the time being, I just want you to bear that in mind. So, it's a kind of strange situation where as this gets more and more parallel, which is a desirable effect, it becomes tougher and tougher to represent it. Now, in the previous case, we were able to prove that a load and a store or two stores were independent of one another. And that gave us more parallelism. Suppose we prove that two of these operations are in fact to the same location, then there's another benefit that derives very often, which is that we can eliminate some loads or stores. In this case, assume we had a store followed by a load with no intervening store. And if we were able to prove that the load was from the same location as the store was too, then instead of reading the value from memory, we could just read it out of the register that we stored into memory. So we could replace this situation by this, where we just do a copy of the value that is in virtual register T1 to the virtual register T2. We've eliminated one load dependence, and this copy, instead of being dependent on the store, is now directly dependent on this operation. So in many cases, particularly if this was in the critical path of the computation, we'd have shortened the critical path, made the computation more parallel. In addition, just by eliminating a load operation, we reduce the memory bandwidth that we require in this machine. Another situation arises where we have two loads that follow a store. And even though we may not be able to prove that these loads are to the same location as the store, if we know that these two loads are to the same address, then we just need to load this once and then do a copy from, say, T2 to T3 to get the effect of the second load. Again, we've eliminated memory bandwidth, though we probably have not made much difference to the critical path length. You can similarly do store elimination. After you've done load elimination, you might end up in a situation where you have two stores followed by one another, one following the other, with no intervening store that could be or is to the same address. Now, if we can prove that these two stores are to the same location, then this first one is redundant, because the value that is stored by this store is not ever accessed by anyone before it's overwritten. And in that case, we can eliminate that store. Again, we get some improvement in memory bandwidth. So the situation here is that by virtue of doing this memory disambiguation, that is trying to prove that the addresses are either equal or not equal, we can benefit either way. If we prove that they're independent, we get more parallelism in the graph. And if we prove that they're dependent, definitely the same, then we can eliminate load and store operations. The worst situation is if we can't prove it either way. So this analysis process of trying to understand whether two references which happen to be in the same basic block are to the same location is the local memory disambiguation problem. And there are three possible answers in general to the question, is A2 the same as A1? One is that they are never equal, and in this case we get better parallelism. We eliminate a dependence edge. The other is that they are always equal, in which case we can do some load store elimination. And the worst situation is the maybe. And maybe comes out of two possible outcomes. One is that it sometimes is dependent, sometimes is not. You can make no general statement. The other is that you just don't know. Your analysis is not powerful enough to answer this question, in which case you'll have to take the most conservative view that it neither is nor isn't. It just may be. There are two types of techniques that you can use to do this memory disambiguation. The first one is using static knowledge. For instance, if we know that two data structures are laid out in memory in such a way that they do not overlap, then we can say for sure that a reference to one data structure cannot be to the same address as a reference to the other data structure. Likewise, data structures that are allocated globally on the stack or on the heap are to disjoint areas of memory. And again, a reference to a data structure that is on one cannot possibly alias with a reference to a data structure that's on one of the other ones. Finally, restrictions that the language places on aliasing can also be used to do this disambiguation. In languages such as Fortran, for instance, the language standard says that if there's a formal parameter that is modified in the procedure, then it cannot alias with any other formal parameter. So with this kind of information, we can make some headway in answering the question, is A1 equal to A2? To go beyond that, we need to do what is essentially symbolic evaluation. And let me illustrate it with this example. Over here, we have a store and a load. And these statements up here compute the address of the store. So we add T1 to T2, get T4 multiplied by C, get A1, and that's the address over here. And similarly, these operations over here are computing the address of the load. Now, trying to answer the question as to whether A1 is equal to A2, we'll go in two steps. First, we do symbolic execution. What we want to know is what the value of A1. Well, we don't know that. but we do know that it is C times T4. Again, we don't know what T4 is, except that it is T1 plus T2. So we can represent A1 in this form as being C times T1 plus T2. Similarly, by doing symbolic execution over here, we can find that T5 is C1 times T1, T6 is C times T3, and A2 is the sum of those two. So A2 is this plus that. So the question, is A1 equal to A2, now becomes the question, is this expression equal to this expression? To answer that, we use symbolic algebra. We start off by expanding this, distributing the multiplication across. So now the question is this expression equal to this expression? We can cancel out like terms, and now we reduce it to as C times T2 equal to C times T3. And there are two ways we can get an answer. One is if C is 0, then these two are definitely always the same. The other is if C is not 0, then the two expressions are the same if T2 is equal to T3. So as a result of this analysis, we can say that A1 is equal to A2, either if C is 0 or if T1 is equal to T2. Now in this case, the answer is still not definite, and we might have to go further back through the program until we get to a point where we might, if we are lucky, see an assignment of T1 to T2, in which case they are equal. Or we might see T1 assigned equal to T2 plus 5, in which case we know for sure they are not equal. But this is the basic method that one uses to try and answer this question. Now, let's move this from trying to do memory disambiguation within a single basic block to across multiple basic blocks. And the question can now be rephrased as is the address A1 that was used in basic block B1, does that refer to the same location as the address A2 that was referenced in basic block B2? And is this the same along some specific flow of control that goes through both B1 and B2? Now we could have asked this as an all paths problem. That is this equal to that along all paths between B1 and B2? But I'll choose to ask it as a single path problem. And as you'll see in a minute, you get much more power out of doing the analysis that way. Once again, we have the same three answers. One is they are never equal, in which case a dependence edge disappears. The other is that they're always equal, where again we can try and do some lodestar elimination. And the one that we don't want to come across, but which we will quite often, is that it's a maybe dependence. Now, in this example, what I'm going to combine is two steps, really. One is the memory disambiguation process, as well as taking advantage of the information that we get from that. Let's start off by considering this load operation over here from the array element x of I minus 1. What we would like to know is this location being referenced the same as this location here, this element of x that was stored to over here. We can repeat this process of symbolic evaluation. I minus 1, when we come over here, we see that I was assigned equal to I plus 1. So we substitute I plus 1 for I. So I minus 1 becomes I. And therefore, x of I minus 1, when moved over here, becomes x of I. So in fact, if we go down this path, the location that was stored to over here and the location that was loaded from are the same. If, however, we went down this path, then these two locations are different. Now, if we asked an all paths problem, the answer as to whether this address is the same as this would come up with a inconclusive maybe. Whereas if we ask it separately along the different paths, we get a definite yes here and a definite no here. We can take advantage of the definite yes by eliminating the load along this path. So conceptually, we move this load up here and here. And this load can be eliminated by just copying from T1 into T3. So that's what we have over here. On this path, the load can be moved up, and since we are now guaranteed that it is independent of the store, we could, if we wish, move it ahead of the store, schedule it as early as we wish. And that's what we have here. The load has moved up along this path over here. So we gain both ways. In one case, we just eliminated the load. In the other case, it has to be there, but we can do it as early as we wish. Now let's consider the other load from the array y, element y sub k. And over here, we have a store to some location y sub j. Again, we'd like to know, are these to the same location? Now here, we'll make use of some additional information, which is that the branch over here branches this way if j is equal to k. So if we can make use of this information to know that on this path, j is not equal to k, and on this path, j is equal to k. On this path, since j is equal to k, then this load is from the same location as this store. We can eliminate it, replace it by this copy operation. On the other path, we are guaranteed now that j is not equal to k, and we can move it up and, in fact, beyond the store. So by making use of symbolic evaluation as well as gathering assertions from the branches, we can get a lot of information about the equality of these addresses, and then use that to either eliminate loads in stores or to rearrange the order. Now, in the case of loops, in the case of special types of loops, we can short circuit a lot of this analysis. The analysis has been pre-packaged for us. And this is the type of technology that was developed by the vectorizing compilers. The types of loops specifically that are admissible are those in which you can rewrite the loop so that so that the trip counter goes from 1 in steps of 1 through n, and where the subscripts can all be expressed as linear functions of the trip count. Now, suppose we have two references again. One, the subscript is a times I plus b, where I is the trip count, and c is and the other subscript is c times I plus d. What we'd like to understand once again is, do we on any location, say store, do we on any iteration that is for any value of I, is this address the same as this address for a different value of I? In other words, on two different iterations potentially, can this address be the same as that one? So if we let one of the values of I be I1 and the other be I2, then the question is A times I1 plus B equal to C times I2 plus D? Or we can rewrite that as this expression. Now, this is the canonical form in which we will try and bring this expression. And at that point, we can bring to bear the techniques of Diophantine equation solving. So once again, this is the question we'd like to answer. And there is a pre-formed solution to this. To get that, we first let G be the greatest common divisor of A and C. And once we have that, we can get our answer never, always, sometimes, based on which of these three conditions is true. If D minus B over here is not divisible by the GCD of A and C, then we can be assured that these two references are never to the same location. If, on the other hand, the GCD does divide D minus B, and in fact, if A and C are equal, then we can be sure that there'll be a consistent equality across two iterations. And the distance between those two iterations is given by this formula over here. And finally, in the remaining cases, that is when A is not equal to C, but the GCD divides this, then there's the potential for two addresses to be the same, but there is no guarantee. So in this case, what we did is we eliminated the steps of the symbolic execution step, because we had a pre-formed solution already in place. Now, here's an example of a loop that falls into the admissible category. The trip count goes from 1 to n, and each subscript is a linear function of the trip count I. And the types of questions we'd like to ask are pairwise. Are any two of these to the same location for different iteration numbers? So for instance, for this address and this address, we can ask the question, is this equal to this? And the answer turns out to be yes for distance 1. In other words, this address on one iteration is the same as this address on the next iteration. And we get that answer by using that GCD test that we just looked at, where if, since these two coefficients are equal and that divides the difference between 3 and 1, therefore it will always be equal, and with a distance that is 1. Similarly, we can ask the question, is this address ever the same as that? For much the same reasons, because the GCD, the two coefficients are the same and divide the constant term, the answer is yes always, and with a distance of 2. However, if we ask the question, is this equal to either this, this, or that, the answer is no, never, using those same tests. Now we can use this memory disambiguation information to go ahead and eliminate loads and stores. The loads and stores that should be eliminated become more obvious if we unroll the first 3 iterations of the loop and substitute the actual values for the expressions. It becomes quite clear that on every iteration except the first one, the load that we have over here immediately follows a store in the previous iteration. So we could eliminate every load except the load in the first iteration. Similarly, once we eliminated those loads, we can find that there are 2 successive stores to the same location with no intervening load. And so the first one can be eliminated. In other words, in all iterations except for the last 2, we can eliminate this redundant store. So let's consider the load first. That corresponds to making use of this memory disambiguation information. And there used to be a load here from ace of 2 times I plus 1. And that's eliminated because it's the same as to the same location as this store from in the previous iteration, which got its register, its value from register S. So instead of the load, we can just make use of the definition of S in the previous iteration. And recalling our EVR notation, we represent that by S square bracket 1, meaning the definition of S from the previous iteration. You should avoid getting confused between parentheses that correspond to array subscripts and the square bracket notation that corresponds to the EVR notation. Having eliminated that load, we can then go ahead and eliminate the store that used to be following this, because on all except the last 2 iterations is redundant. However, on the last 2 iterations, that store is not redundant because there is no iteration 2 following. And so those last 2 stores have to be done after we exit the loop. And similarly, this load that we eliminated was redundant on all but the first iteration. And on that first iteration, we still need to do that load. And we do that before we enter the loop. So the net result in this example is that a loop that used to have 4 loads and stores has been reduced to a loop with just 2 loads and stores, which is again an improvement both in memory bandwidth as well as in some of the critical paths that run across the iterations. Now, that the class of loops that we're looking at, the so-called admissible class for which the vector disambiguation technology was applicable, is a very important class of loops, but by no means is it the only type of loop we'll encounter. Here is a little example, and in fact this is kernel 24 from the Livermore-Fortran kernels. And what we're trying to do is to find the index of the smallest element of the array X. And to do that, what we're doing is we are sweeping through the array. K is sweeping through all the elements of the array. And on each iteration, we load the test element as well as the current smallest element, compare them. And if it turns out that this is smaller than that, then we replace the index, the smallest index, with K. Now, we could once again if just inspecting this intuitively, it becomes clear, it's obvious that on most of the iterations of this loop, we will not find a new minimum. And therefore, in fact, neither x of m nor xm over here changes. And there's some redundant loads going on here. Now, we can use the same process of symbolic evaluation. We can take this x of m, conceptually take it around the back edge until it comes over here. Now, if we do not, if this condition is not true, then m is unchanged, and in fact, it's already available. If this condition is true, then m gets changed to k. And so now we need the new x of m, but that is the same as x of k, which is available. So we can end up with this kind of code over here, in which we don't keep loading x of m repeatedly. And in the situation where this condition is true, when we find a new minimum, we set m equal to k and we set xm equal to xk. Now, in this particular case, we used to have a load on a recurrence path, which could increase the, or rather slow down the loop significantly. And by eliminating it, we get a big speed up. In fact, most compiler vendors tend to try and find this situation as a pattern match, since it's a very important benchmark. And when they find this kind of a pattern, they replace it by this. But the point I'd like to make is that by using the symbolic evaluation, you can do it in a systematic fashion. So far, we've been looking at arrays and disambiguation in arrays. And that is the area where there's been most progress. That's the part that's most amenable to analysis. But there are lots of programs which operate by dereferencing pointers. And the big problem is that in languages such as C, if one really wished to, one could have a pointer that could point essentially to anything. And it would be quite impossible to tell whether the location pointed to by one pointer was the same as the location pointed to by another pointer. You'd essentially be able to prove nothing. Now, in some cases, if a pointer is being used much like an array index, so if you have a pointer into an array and you're bumping that pointer by some value, then you could try and make use of many of the same analysis techniques that we've seen. But in general, when you're working with dynamically declared data structures, dynamically created data structures, what you will have are pointers that are embedded in those data structures. And you'll need to answer questions about the equality of pairs of those pointers. And in principle, this would seem to mean that you have to symbolically evaluate all of these pointers that are embedded in data structures. And the number of these pointers is arbitrarily large depending on how large this data structure became. It would seem to be an impossible problem. The approach that is being taken over there is to build up a kind of an algebra that tells you what the geography of this data structure is. By this I mean in an array, a two-dimensional array, we understand how different elements are related to one another. So we know in particular that if I have an index into a particular array element, and if I increment that by 2 and decrement it by 1, that points to the same location as if I just incremented by 1. We know that about the geography of an array. The question is, in a linked list data structure, which has forward links called flink and backward links called blink, how do I understand that if I traverse 3 flinks and then 2 blinks, that is the same as having traversed only 1 flink? So you have to develop an algebra for each data structure that is custom to that data structure to be able to reason about these things. And this is very much on the frontiers of research in this area. So let's say at this point we have brought to bear all the analysis that we know how to eliminate all the spurious anti-dependencies between due to register usage and due to memory usage. And if at this point the amount of parallelism we have is inadequate, then we will need to try and restructure the computation so that it has more ILP in it. We've already seen a couple of ways in which this is done. For instance, speculation and predication consisted essentially of ignoring some of those control dependence edges between the compare and the operation, or between the operation and a merge. And by ignoring those edges, we collapse the critical path through the computation, we increase the amount of ILP. Similarly, load elimination, when it's on a critical path, again collapses the depth of the graph and increases the ILP. But eventually we'll have to resort to things which really restructure the nature of the computation quite significantly. And the two things I'd like to talk about are algebraic transformations and control height reduction. Now imagine that we had some expression tree in which we multiply a whole bunch of operands, and then we take the results of the operands and then we add them together through this adder tree. Also, let's say that the critical path in this computation, the path that we are sensitive to, runs along this black set of edges. What we'd like to do is reduce that critical path and make the computation more parallel. So what we can do here is make use of the laws of algebra. And since additions are commutative, we can view this computation as being essentially one of doing all the multiplies and then just summing all of those using a sigma function. And the significance of the sigma function is you're not specifying the order in which you do these additions. Of course, what we'd like to do is to create an evaluation order that minimizes the critical path through the along the black edge. And the way one would do it is to add up as all the multiplies results except for this one first, and then take the result of that and add it to this. So what we'd get as a result is this computation where first we add up the results of all the multiplies except for this one, and then finally we add that to this. So the critical path length has gone down from, in this case, 1 multiply and 4 adds to 1 multiply and 1 add. And once again, what we are making use of is the law of associativity for additions. Now, in this example, we have a sequence of interleaved multipliers and adds along the critical path, with a multiply feeding into an add, feeding into a multiply. And because we don't have the multipliers together or the adds together, trying to use associativity to reduce the critical path length will not work for us. What we need to do is to first get the two multiplies together. And to do that, we invoke the distributivity of multiplications over additions. And we will copy this multiply by d into the operands of both operands of the add. So what we will get is the computation over here, in which this addition corresponds to this addition over here. This multiplication corresponds to this multiply having been copied over onto this operand here. And lastly, this multiplication corresponds to that same multiply copied over into the other operand. So now the computation that we have is in the form that we like. There are two multiplies together which associate, and two additions together that associate. So we can look at that computation in this following form. Namely, we first need to multiply 3 terms together in whatever order is most convenient. And then we need to add 3 terms together in whatever order is most convenient. And the order that we'll choose is the one that minimizes the critical path length. So we'll play the same game again. We'll perform all of the multiplications that we need first. And then in this case there are only 2, and then take the result of that and multiply it by a. And likewise, we'll first add these 2 terms and add the result of that to this result here. And we get this computation here, which once again has only 1 multiply and add on the critical path, whereas the original computation had 2 multiplies and adds. Notice that this critical path reduction was at the expense of increasing some other computation path. And presumably that path was not as important. Also, notice that we added an additional addition operation into this computation so as to be able to reduce the critical path length. And this is a phenomenon that we will see quite often, namely in the process of trying to make the depth of the computation graph less, namely make the critical path length less. We will actually add computation to it, increase the total amount of computation. And to a certain extent, this works out to be a winning strategy. Now, just as we can use algebraic transformations within acyclic code, we can do that within loops as well. And I won't go through the entire detail, but here's the situation. What we are doing is on each iteration of the loop, we are multiplying two terms and accumulating the result, the product, into this sum. So what this says is that the sum on one iteration is the sum from the previous iteration. Once again, we're using the EVR notation, plus the product that was just computed. Now, since each addition feeds the addition on the next iteration, we can't have the iteration starting sooner than one every add latency. Now, what we can do is make use of the following back substitution. Since S is equal to S from the previous iteration plus the product term, so we are just looking at restating this. Therefore, this must be true on the previous iteration as well, in all cases except if we are talking about the first iteration. So S square bracket 1 is equal to S square bracket 2 plus P square bracket 1. And now we can take this expression and substitute it for S1 in this expression. So we get this over here, that S is equal to S2 plus P1, namely this expression, plus P. And then we can reassociate the addition to get it in the following form, that S is equal to S from two iterations ago plus this term. So now, since each add feeds into an add two iterations later, not just one iteration later, we can actually perform an add every half add latency, or two iterations. We can perform an iteration every two iterations every add latency. And we've doubled the performance of this loop. Once again, there's a little bit of bookkeeping to be performed. On the first iteration, this is not true, so we have to peel off the first iteration of the loop, and that is what this code over here corresponds to. But from the second iteration onwards, we are able to run it twice as fast as we'd have been able to otherwise. In many cases, and definitely an example that we looked at previously, we added to the amount of computation so as to reduce the critical path length. There are some important cases where you actually do not add to the amount of computation. Here's the case of an induction variable that is being incremented by 4 each time around the loop. Now, we could go through precisely the same process as before. The only difference is we are adding 4 each time rather than the result of the multiply. And if we went through the same process, we'd have an additional term here, which is adding 4 plus 4 to get 8. However, this is a computation that we can perform at compile time. We can eliminate that add and just add 8 directly. And so now what we're doing is, instead of adding 4 each time to the value in the previous iteration, we now add 8 each time to the value from 2 iterations ago. Again, we potentially double the speed at which this loop can be executed, and with no extra computation cost. Now, a couple of points I'd like to make about algebraic transformations. One is that that you can potentially alter the results of the computation. If, for instance, you are taking the difference between two numbers that are very, very close in magnitude and then multiplying it by a large number, the result that you get can be quite different than if, for instance, you multiply those two numbers first by the large number and then take the difference. And these kinds of restructurings are what we've been doing in all our algebraic transformations. And there is the potential that in certain sensitive computations, the numerical stability will be damaged. For precisely the same reasons, there's also the possibility of spurious exceptions. If the numerical precision can be harmed, then it's equally possible that you might run into an overflow or a divide by 0 as a result of the loss of precision. And this is particularly problematic because this is absolutely not an exception that should have occurred if you had not done this transformation. So this makes the whole transformation look fairly unsafe if we are not careful about it. In the example that we looked at, we assumed that none of the intermediate results of the computation were used by anyone else. If in fact they are, we have to make 2 copies of that common part. And then 1 copy will participate in this restructuring, and the other part will compute the result that is used by some other operation. Another point is that it's unlikely that we'll find these lengthy expressions within one basic block. Typically, they're spread across multiple basic blocks. And so before we can apply these algebraic transformations, we essentially have to collect all of them in one basic block, perhaps using speculative execution. The last point I want to make is that even though the example that we looked at had to do with addition and multiplication, this technique is equally applicable to other sets of operations. So for instance, ands and ors behave the same way. The min operator is associative. And in fact, the same philosophy can be taken to a totally different domain, namely reducing the control height. Here's an example of some code where, let's say we've done extensive speculation and moved all the operations up there, but we still have these branches that are left, and they have to be in sequence, because even if this condition B is true, we can't branch off to LB if in fact condition A had been true, because in that case we should have gone off to LA and we should never have seen this branch. So correctness requires that these branches all be serially linked one after the other. Now suppose the situation was such that these branches were almost never taken, and that this was the first branch that really had a significant probability of being taken. What we'd like to do is to quickly determine whether any one of these branches are going to be taken by saying if A or B or C, then we'll go somewhere else and then determine whether it's which of these 3 branches should have been taken. And if this is not true, then we fall through and then we get to this branch as soon as possible. So the net result is that most of the time we will go through this way, because these branches, remember, tended not to be taken. And we get to this branch with just 1 branch delay rather than with 3 branch delays. So the philosophy is quite similar, even though obviously the algebra is quite different. The philosophy is one of taking some amount of the computation, in this case is the branching computation, and moving it offline so that the critical path is reduced. I'd like to now move on to the topic of how one builds ILP compilers. There are 3 major issues that one is trying to optimize simultaneously when one builds a compiler. The first one, the one that we've been focusing on all along, is the code quality. In this case, the schedule length, the computation time. But we also have to pay attention to the compile time complexity, namely the amount of time it takes to compile a program or the amount of storage that it takes. And finally, we've got to consider how long it takes to design the compiler. If an algorithm is so complicated that it's not ready in time for shipping the compiler, it's of little use. Or likewise, if the amount of code quality improvement is rather small compared with the investment, then one will most likely not bother. There are 3 key decisions that one has to take. One is the choice of the algorithm that one selects. And there's a trade-off, an obvious trade-off between the quality of the code that you get and the algorithmic complexity. The 2 things that I want to talk about more are phase ordering and the intermediate representation, and how these play together. This is a style of diagram that I'll be using quite a bit in the next few slides. So let me just explain to you how to read it. Across the columns, we have the different pieces of the program that's being compiled, that we are in the chunks that we are considering them. In this case, we are considering basic blocks. So we have the different basic blocks of the program lined up across the columns. Over here, the row headings are the different compiler actions. So in this case, it's global optimization followed by global register allocation. The arrows within this tell us in what order these different compiler activities are performed upon the basic blocks. So what this says is that the global optimization consists of optimizing this basic block and this basic block and so on, and then perhaps repeating this a number of times. And then finally, when we are satisfied with it, we'll do global register allocation. Now, this is the other part of the diagram I'd like to call attention to is the nature of the IRs that we're using. And in general, every compiler phase has some private data structures that it uses. But what I'm focusing on is the information that passes from one phase to the other. And the conventional IR is an n-tuple form. Now, this might be the traditional backend of a compiler, where each compiler action is performed on the entire program unit before you move on to performing the next action. And this has been called a phase-ordered compiler, because each phase, you have a phase of doing global optimization followed by a phase of doing register allocation across the whole program. Now, suppose we consider a compiler in which there's an attempt to do some amount of scheduling in a small way, local scheduling only. It might be natural to extend this phase ordering by adding these additional phases over here. First, a scheduling phase, which schedules all the operations. Then a register allocation phase, which does the register allocation based on the schedule that we have obtained. But in the process of doing the register allocation, we might need to insert spill code. And to handle that, we go through a second pass of scheduling. Now, this is just one way of structuring it. But we now get the benefits of simple local scheduling. And it you might imagine that was quite natural to extend the phase ordering to have these additional phases. However, when you go to an ILP compiler, you end up with a rather profound change in the organization of the compiler. And this is all driven by the fact that global scheduling has been elevated to a stature of very great importance, that is the key to high levels of ILP. The second fact about global scheduling is that it requires a dependence graph. All scheduling requires a dependence graph to have been constructed. And global scheduling requires the dependence graph of the entire program unit to have been constructed. So now let's, and the third point to be made is that if we want to have a good, high quality graph with as few edges as possible, we need to do memory disambiguation so that we can eliminate the dependence edges due to loads and stores. Now, it might seem natural to extend the phase ordering idea. What we've got here is a global scheduling and register allocation phase that combines those three phases from earlier on just for economy. And preceding that is a phase in which we do global memory disambiguation and followed by building the graph. So the idea is that we first do the optimization, then we do memory disambiguation, build the graph for the entire program unit, and then we'll go ahead and do the global scheduling and register allocation. The problem is that memory disambiguation is firstly very expensive, and the larger the program or the piece of the program that you're working on, the larger the number of pairs of loads and stores for which you have to answer the question, is this equal to that? Just the number of pairs obviously goes up quadratically. The expense of doing global memory disambiguation goes up by as a much faster, larger polynomial. So first, this is represented by rather large dots that are supposed to indicate that the computation time, the compile time, is increased. Perhaps even worse is the fact that the amount of output from memory disambiguation, whether it's in one form or the other, whether it's represented in the graph or not, becomes truly voluminous. And so you have a huge data structure that has to be stored and carried through the global scheduling phase. In practice, this is fairly unrealistic. And we have to cope with this fourth fact about global scheduling, which is that the output of global memory disambiguation is just too large to store that for the entire program unit. What this says is we have to have a way of consuming this information as it's being produced. Now, the complexity of global scheduling itself is such that one typically wants to do region-based scheduling, by which I mean take some small part of the program unit, either a trace, a loop, or whatever, and schedule that before moving on to another region. And so what would make sense is to just do the global memory disambiguation for that part of the program, the region that we're going to schedule. So this leads us to the following type of structure. Now over here on the column headings, we have region 1, region 2, etc., where a region, as I said, could be a trace, it could be an innermost loop, it could be an if-converted region, etc. And over here, the compiler actions are much the same as we had in the previous slide, except we've got an action here called region picking. So the way this compiler operates is you first go ahead and do all your global optimization. Then you come over here, pick a region. For that region, you do the memory disambiguation, build the data dependence graph. You do the scheduling on that region, and then you can throw away the dependence graph. Meanwhile, the rest of the program has been sitting here in the n-tuple form, while just this one region was translated into the graph form, which is far more expensive. But since we've limited it to just one region, it's tolerable. Once we've finished that region, we'd go back, pick another region, and repeat the process. So we now have a situation where, unlike the traditional compiler, which tried to perform one phase on the entire program unit, we now have a situation where we perform a number of actions on one region at a time. Now there was one fact that I didn't mention, which I should now, which is that global scheduling tends to create code generate new code. In the case of trace scheduling, there's this compensation code, which results after we've done the trace scheduling and we have to do the compensating copy operations, duplication of operations. In the case of the modulo scheduler, there are the prologues and the epilogues that are generated after scheduling. And we would like this new code to benefit from all the optimization that the original code benefited from. Because by the time we're through with all of this scheduling, code replication, it could well be that a very significant fraction of the code at the end was generated along the way rather than originally. And so it has not yet been optimized. So as to be able to optimize the code that is created as the result of scheduling, what we do is we add these two phases to the structure that we already had. So down here, following the scheduling, we have the code replication phase. And we will generate the new code that has been created in the same IR that we had originally when we were doing optimization. The other thing that we will do is that we will add an additional phase following region picking, which does optimization over that region. So this is much like global optimization, except that it's restricted to the region. So the idea now is you pick a region, you optimize it, you do the memory disambiguation, build a graph, schedule it, create any new code that's needed, and now go back and pick another region. Now, every piece of code gets optimized only once. You only optimize the code that is going to be scheduled. And once you've scheduled it, it's out of the picture, and you never optimize it again. So this leads to getting the benefits of optimization, global optimization, but without having to do it repeatedly over the entire program unit just because a little new code got generated. However, even though we can try and do the optimization in a manner that is constrained to operate only within the region, the analysis that supports it has to go beyond the region. For instance, whether a particular variable is live is not an answer that can be answered, is not a question that can be answered by just looking within the region. You might have to trace it out across the entire program unit to see whether there's another use of that particular result. Similarly, the symbolic analysis that is needed to support memory disambiguation also has to go out across the entire program unit. So we have this phase over here, which does operate over the entire program unit, tries to do all the analyses that support the optimization, the regional optimization, the regional memory disambiguation. And that does lead to the question of whether the same problems that we had with memory disambiguation will resurface. In other words, is the volume of the information that's generated by this analysis so great that it is going to be difficult for us to maintain it, store it, maintain it, and keep it up to date as the rest of the code goes through these different modifications. This is not clear, and it's again a matter that is being researched right now. However, in assuming it's workable, we will need an IR over here that is somewhat richer than the standard n-tuple IR to be able to embed all this information in it. And we'll need the graph IR, which is restricted once again to just one region at a time. What we are involved in here is considering engineering trade-offs. This is very much an engineering issue, not a purely algorithmic issue, not a theoretical issue. And what we're trying to achieve is the best trade-off between effectiveness and complexity. We'd like to hit the 80-20 rule. And one obvious aspect of that is just the algorithm selection. There are algorithms which have much greater complexity, but which don't buy you that much more than other ones. But the point that I want to make here is this issue of subdividing the program unit into smaller units to control the complexity. Let's say we have an algorithm that is n cubed in complexity. If this is the size of the program unit, then the volume of the cube represents the amount of computation we have to do. If we divided this program unit up into two regions, then since this is an order n cubed complexity, we'd reduce the amount of computation by a factor of 2 squared. In general, if we divide this up into m regions, we would divide the complexity by m squared. In a typical program unit, the number of regions we might expect to have would be in the many tens, and m squared is a really respectable factor. You could go still further and divide it down at the basic block level, and again the total computation cost would drop by another significant factor. That has to be traded off versus the code quality. We know that trying to do things like optimization, scheduling, etc., just at a basic block level just is not very effective, and that if we do it globally, that we get the maximum benefit. The experience is that over meaningfully defined regions that you get most of the code quality benefits without paying the entire price. And this is one major thing that region-based compilation does for you. Now, this has been something that has been in place for global scheduling for a while, so-called global scheduling. And in fact, recently for register allocation, etc., there's a trend in this direction. So let me just summarize this, the last sequence of slides. The first point is that global scheduling is of key importance in an ILP compiler, and it changes the organization structure of the compiler in quite a profound way relative to a conventional optimizing compiler. And the second thing is that global scheduling and memory disambiguation, we know from experience, have to be done in a region-based fashion. Trying to do it globally across the whole program unit is just not practical. Somewhat more speculatively, perhaps region-based scheduling can be step-by-step extended to the earlier phases, including optimization and so forth. But this is something that we don't yet have that much experience on. But to repeat the benefits of region-based compilation, in comparison to doing it locally on a single basic block level, it's much better. But the compile time complexity is much less than doing it across the entire program unit. If the regions are selected in a frequency-sensitive fashion, and the most frequent ones are processed before the less frequent ones, then we get frequency-sensitive compilation. In the case of optimization, for instance, we would optimize the more frequent regions at the expense of the less frequent regions, which is probably something that is desirable. And finally, the design complexity is contained as well. We have to only develop algorithms that can operate over relatively small code structures, such as traces or innermost loops, rather than something that can handle an entire program unit. So now let me just wrap up the talk. The first thing I want to point out is that there is a fairly significant difference in the ILP mindset. The primary metric, as I mentioned, is the schedule length, and issues such as operation count, register pressure, etc., are important but of reduced importance relative to a conventional optimizing compiler. We are at times willing to actually increase the operation count so as to reduce the schedule length. Because the schedule length is a key issue, there are a number of compiler techniques that are needed that are all focused on reducing the length of the critical path through the computation. And finally, global scheduling, as we've just seen, is key to the whole ILP compiler and has a tremendous importance on how it is structured. In the course of this talk, we have talked about a number of new technologies that are important to ILP. The parts that are most frequently discussed and where you see the most literature has to do with scheduling. And that in turn depends upon doing dependence analysis between loads and stores, which in turn depends on doing good memory disambiguation. Over here, we have the load store optimizations that we've looked at, which are in many ways similar to partial redundancy elimination, but operate on loads and stores. That in turn requires data flow analysis between loads and stores, which in turn depends upon memory disambiguation. We have path length reduction techniques such as the algebraic transforms, which depend in ways that I could not get into on being able to manipulate if converted code and optimize it, etc., in much the same way that you can today handle code which is in the control flow graph form. Memory disambiguation in turn depends upon symbolic analysis, and symbolic analysis depends on information it has about the data structure's geography, which it gets either from data declarations or from having to do data structure analysis. Now, and finally, we have the IR, which ties all of these together for the information flow from one action to the other, and a machine description, which is key to a number of these activities. Scheduling is very dependent on having a good model of the machine, and that comes from the machine description. Similarly, path length reduction needs to understand the latencies of operations, and so forth. Just a comment on the level of maturity of this field. The parts that you see in green are the parts that are pretty mature, by which I mean if there was little further research in these areas, we could still get by. The parts where there's been a fair amount of work are the blue regions, but whereas there's been a fair amount of work, this is by no means a closed topic. There is lots of additional work that needs to be done in the blue areas. And finally, the red areas are the areas where there's been very little work done. And all of this needs to be put in place to have the ultimate ILP compiler. Even though I've spoken about quite a few technologies, there's a lot of other stuff besides which is pertinent to a high-quality compiler in general, ILP or otherwise. And I won't go through all of these in any detail. I just wanted you to be aware that there are a number of issues besides this. And the one point I want to make is that to a large extent, the amount of ILP that you can get is not only a function of the compiler technology, but of certain key architectural features that make it easier to enhance, exploit, and expose ILP. A question that one is almost always asked to comment on are what are the limits of ILP? Eventually, how much will we find? How much is there? Just a couple of comments around that question first. The first point that should be obvious is that the achieved levels of ILP that have been seen on products that have been built are clearly an upper bound, clearly a lower bound on what can be achieved. What we have found is that in the case of numerical codes, loop-oriented codes, that the levels of ILP are actually very high, in the many tens, in some cases much more. In the case of the so-called scalar codes, systems codes, things of that type, the experience so far has been that the levels of ILP are the level of about 2 or 3. However, we should bear in mind that many of the techniques that we've been discussing today have really not been applied when those measurements were taken. And the issue really is when we perform all the research that is currently being performed on finding ILP in scalar codes, how much ILP will we find at that point after the technology is in place? There have been a number of studies that claim to be limit studies. And in general, the flavor of these has been, I did this, I measured it, I found so much ILP. It should be clear that all such measurements tend to be low bounds, really, because they are existence proofs that there's at least that much. However, in many cases, there have been rather generous assumptions made about the memory disambiguation that's possible. For instance, assuming that you can do perfect memory disambiguation. So the net effect is that these so-called limits are really upper bounds on lower bounds, and as such, they really mean very little. What we need to understand is once we have done this research, once we have developed the technology that needs to be developed, how much will there be? And to be quite honest, we just don't know it today. It's too early to tell. So where does this leave us? From the researcher's point of view, I think it's fair to say there's a wealth of opportunity. There's a lot of technology that needs to be developed, to be researched. But I think researchers need to go about doing this work much more methodically and carefully. Very often the research is done with rather unrealistic machine models in mind, and that really is not helpful at all. Very often again, techniques are suggested which are claimed to be very good, but very little attempt is made at measuring them, actually characterizing them, still less effort in comparing them to the alternatives to understand what the relative merits are. And lastly, there's been very little emphasis on the practicality of the techniques, on whether anyone would ever want to engineer them into a compiler. From the industrial perspective, I think one has to say you have to proceed with caution in the ILP field. As we have seen, the field is rather immature. There's a lot of technology that's still to be developed. There are lots of opportunities for sure, but we don't yet know which of these will pan out. On the other hand, what's the alternative? If what one wants is to maintain the rate at which microprocessor performance has been speeding up over the years, approximately a doubling every 2 years, and if we want to do that without having to rewrite programs, new algorithms, new languages, then the only alternative appears to be ILP. And so the message would be to really emphasize making this go ahead as fast as possible, to allow the research to go ahead as fast as possible, because right now we do see no other alternatives at the level of microprocessor architecture. In the rest of the tape, you will find references that will help you get started in doing further reading on the topics that I've discussed, plus a pointer to a more extensive bibliography that you can access.